Welcome. This presentation concerns the impact of temporary well shut-ins on unconventional reservoir performance. We will begin by describing our approach to the problem of quantifying the impact of temporary well shut-ins on the order of 3 to 6 months on production and reservoir behavior. We will then discuss in detail the dynamic stress and reservoir property changes in the subsurface during shut-in. Finally, we will describe in detail the well performance implications of temporary shut-ins on wells in the Williston, Delaware, Midland, Eagle Ford, and Osage reservoirs. Approach. Our aim is to understand and explain the expected well performance after temporary shut-ins and the changes in reservoir properties during this period. Example reservoir simulation models for a subset of unconventional reservoir systems were created based on Nitec's institutional expertise and understanding of a range of different unconventional resources. Simulations were performed with and without shut-in periods to provide a basis for comparison. 3 and 6 month shut-in periods were tested. All simulations were performed in Ridgway Kite's 6X simulator. The 6X simulator is a dual porosity simulator with pseudo-geomechanical tables which model the dynamics of rock breaking through tensile and shear deformation and the subsequent closure of the fracture network during well production. All results were processed and visualized by Nitec's Lynx software suite. Results are not representative of any specific well or asset. Stress and property changes during shut-ins. There are multiple specific possibilities regarding the expected dynamic changes in the near wellbore region of the reservoir during a well shut-in. First, pressure and fluid distributions are expected to change due to equilibration. Next, local stresses within the stimulated reservoir volume will shift as the fluid and pressure distribution shift. Additionally, the distribution of connectivity within the stimulated reservoir volume will shift as a consequence of the altered stress distribution. Finally, proppant placement and distribution can be expected to change. Here we examine the water saturation distribution in the fracture network for a pair of wells drilled in a Permian unconventional proxy reservoir system immediately after shut-in, at the end of shut-in, and after 2 months of resumed production. The change in water saturations, especially in the fracture network, will be mainly a consequence of buoyant equilibration. Water will settle downward into deeper zones and accumulate in the stimulated reservoir volumes of deeper wells. When production resumes, the deeper wells will see a disproportionately high share of water saturation and thus water cut, but will eventually return to the baseline water cut value. We now examine the stress distribution in the reservoir at the beginning of shut-in, at the end of shut-in, and after 2 months of production. Higher net stress is observed around the wellbore during depletion. The net stress then diffuses and equalizes across the reservoir during shut-in as the pore pressure equilibrates. After 2 months of resumed production, net stress has once again increased around the reservoir, but in a distinctly different and more diffuse pattern. As previously mentioned, stimulated reservoir volume connectivity and effectiveness change during shut-in as well. At the beginning of a shut-in, stable stimulated zones are evident around each well. At the end of shut-in, connectivity within the SRV has in fact increased as the net stress near the well has decreased, permitting the fracture network to open up elastically. Net stress equals breaking stress minus pore pressure, so the equilibration of pore pressure reduces net stress. Finally, SRV connectivity drops back to approximately its previous distribution after 2 months of subsequent production. Expected well performance from different basins. First, we examine a well in the Bakken. We compare the default performance of the well, experiencing no shut-in, represented by the black line, to the performance of the same well with an imposed 3-month shut-in, represented by the blue line. Observe that the bottom hole pressure gradually rises during shut-in as a consequence of pressure buildup due to support from outside the SRV. This pressure buildup results in a significant rate boost when the well is reopened, which then diminishes back to the baseline trend within a couple of months. A slight increase in water cut is also observed before a relatively quick return to the pre-shut-in value. Next, we examine a Three Forks well. Again, we observe a rate boost subsequent to the 3-month shut-in. The water cut actually diminishes in a sustained and long-term fashion here because during shut-in, water slumped down through the fracture network into the lower Three Forks. Now we will discuss a pair of wells drilled in the upper and lower zones of the Delaware. First, we examine the upper Delaware well. The pressure buildup results in a remarkable boost to liquid rate. In this case, an ongoing reduction in water cut for this well is due to the presence of a deeper well which drains away the slumped water. Now we examine the deeper of the pair of Delaware wells. A less significant liquids rate boost is observed post-shut-in, with a relatively negligible change in oil rate. The increased liquid rate is due to the water slumping through the fracture network into the deeper zone. For a well in the Midland Basin, there is a reasonably good boost in oil rate after shut-in, accompanied by a transient spike in water cut. The overall well performance returns to its default trend within a few months. Finally, in the Eagle Ford, oil rate and liquid rate both increase significantly for a short period after shut-in, but then essentially resume the prior decline trend. One issue that might be important but not tested for Eagle Ford is the presence of bentonite. If the shut-in commences immediately after hydraulic fracturing, the injected fluid will have more time to contact with the shale in the reservoir. If bentonite is present, swelling may occur, reducing the expected hydraulic fracture productivity. Thank you for your attention. If you're interested in finding out more about the services we offer, please contact us at solutions@nitecllc.com or visit our website at www.nitecllc.com.